I've longed to do a presentation on the science of musical sound. As some of you know, Ron and I used to pack up the equipment and take it to grade schools and put on a science program for the children. But I've never done one exclusively on sound, and I have a particular interest in that. So I've tried to put something together that does that. The short time I had, I wasn't able to prepare everything I needed, but there's enough here to keep us busy for a little while, I think. It might seem at first that the science of musical sound is sort of a misnomer. Science is very specific. It's numerical, it's quantitative, it's unambiguous. And music, though it has mathematical relationships, is probably more aesthetic, psychological, subjective. But there is a very close correlation between the two. I hope we can demonstrate that this morning. First, we have to talk about sound, I think, since music is essentially sound. And, well, what constitutes sound? Well, actually, anything that vibrates will produce sound if it's within the right spectrum of our hearing. Simple harmonic motion is what we... as soon as I can find my weight. Getting too old for this. Well, I've had a lot of birthdays since I've retired, and it shows. If I hang a weight on a string and I displace it from that equilibrium position, it'll bounce back, go through the equilibrium position, bounce higher, and then go back again. And it will keep doing that until the waves damp out. Now, it's not producing sound because it isn't fast enough, and it doesn't pump the air hard enough for us to be able to get a signal strong enough to hear. But anything that vibrates will produce, or I should say any sound that we hear emanates from something that is vibrating with simple harmonic motion. But that's not the only thing we need. We need something that will amplify that sound to the right level so that the auditory nerves can respond to it. For instance, if I wind up a little musical box unit here, can you hear that? Not too well. That better? So we need something to transmit the sound. And in order to have sound, we need a body that vibrates. We need a medium through which it... that's enough, thank you. We need a body that vibrates. We need a medium through which the sound waves can be transferred. And we need a receiver of the sound. Now, sinusoidal waves are generally what are produced by many bodies. Of course, all of this you already know. If you've had science courses, this is all familiar stuff to you. That would represent a sine wave of anything vibrating. But many things can vibrate and produce sound that can be transferred into musical sound. I have a hacksaw blade here, and if I hold it down tight enough, we used to, I remembered when I was a little feller, or when I was younger, that is, when we had substitute teachers, we used to take bobby pins and stick them in cracks in the desk and twang on them, you know. And some of us would actually play a little bit of melody if we got cooperation among a number of us. I want to show you what a wave really looks like. If I set this string in vibration, and if the lights get dim enough so I can see what I'm doing, we should be able to show you. So what you saw was something like this. A wave bends in one direction, or the string was actually displaced in one direction like that. Then it reflected back on itself and produced what we call a standing wave. With a strobe light, you were able to see that actually the string was bending in that fashion. We have a pair of tuning forks here. Where'd you put it, Ron? Sorry, I'll use this. Oh, thank you. These are tuned, both of these resonators are tuned and both of the forks are tuned to the same frequency. If I strike one, I can set the other one in vibration. This is an important concept in music too, where we have sympathetic vibrations. That is, one vibration can set another one into vibration if they're matched frequencies. Also, I'm depending upon the box to be tuned, or you wouldn't be able to hear it that well. It's a resonator. So it's not enough just to have something vibrating. We have to have the level high enough so that it can be heard. That reminds me of the typical philosophical question: if a tree falls in the forest and there's no one around to hear it, is there any sound? Well, how do you answer that? Well, it depends on your definition, of course. If your definition of sound is matter set into vibration, then of course, yes, there's sound, according to that definition. If you're defining sound as the stimulation of the auditory nerve, then of course, if there isn't one available, then there is no sound. The human ear is a magnificent piece of equipment. It is very sensitive. I don't know if you're interested in these levels or not, but the equation for the level at which we can hear sound is given by, let's say, sensitivity, intensity level is equal to 10 times the log of I over I sub 0. And this is in decibels. And the range goes from 0 to 120. Zero level is called the threshold of hearing, which is 1 times 10 to the minus 12 watts per meter squared. That's not very much energy, and yet we can hear an intensity in air of that amount. Then it goes up to, that amount is 1 watt per meter squared. Now, since sound is a radiant energy, it behaves as all radiant energy does. If we imagine the energy spreading out from a surface like that, we're talking about the energy that goes through 1 square meter perpendicular to the direction of propagation, and that's how we describe the energy. If we go out twice as far, when we double the distance, if this is 1 and now this distance here is 2, doubling the distance reduces the intensity by 4. Well, the square it in. If we triple the distance, then the intensity would be 1/9. I'm concerned about what we call a threshold of hearing, and this decibel scale that goes from 0 to 120. Continuous loud noises can damage the hearing system. Modern music borders on 120 decibels. We were to a wedding reception not too long ago, and we surveyed the area, and lo and behold, I was set at the table directly in front of the big speaker. So I talked to the middle-aged man that was the disc jockey. He was in showbiz. And he says, I know how to do this. I've done it for 30 years. I was asking him to keep it low, you know. Well, he didn't keep it low, but that's probably because he's deaf. He's done it for 30 years. And I'm continually concerned about these people that go by with 200 watts of power blasting from their automobiles. You can hear them coming, you can hear them going. And I'm afraid that many of our young people today are going to be deaf at a very early age. But this is an extreme. 120 decibels is a very loud noise. In fact, it borders on pain. It's no longer the sound, it registers pain. Let's see, what else do we need to know? I have some other things I'd like to set in vibration to show you that anything that vibrates can be made to sound like music. I brought my harmonica along. I got a chain on it so I don't swallow it. And of course, what we have here is little pieces of steel that are set in vibration by a blast of air. You've heard of a Stradivarius. This is not one. This is a Cigarius. Well, it's a cigar box violin. I really have to tune it to start with. Well, I have to tighten the string. It tends to stretch. I'm going to play for you an arrangement of my own composition. I call it my own arrangement of my own composition. Mr. Perlman, eat your heart out. Well, it's not a catgut. When you consider a real violin, it's amazing that you can take a piece of a tree, stretch across it the innards of a cat, and draw across it the pieces of a tail of a horse and get beautiful music. Well, I didn't have those elements, only the wood. That's a piece of plastic, and so is this, and so it doesn't produce the vibrations that a good violin would. But the important thing is that in order to have sound at all, there has to be a resonator, a sound box, in order to translate the vibrations into impulses strong enough to beat the air so that the impulses can reach the auditory nerve of the ear and strong enough energy to respond. We call that, let's see. I should have used the black one for this. I'll use the black one now. We call that impedance. I feel obliged to use the board since I was a teacher for so long and it's hard to get out. Impedance matching. It's sort of a translation between the vibrating device itself and the medium through which that sound has to travel. So technically then, the string is doing the vibrating. The box itself is the impedance device, and it translates or augments the vibrations so that they're strong enough to push on the ear so that that impulse goes through and reaches the ear. The impulses that we deal with are called longitudinal waves. This is a transverse wave because the displacement is at right angles to the direction of propagation. Pretend you can read that. Sound waves, however, are really different. They're very hard to draw. And so we don't usually, now those are called longitudinal waves. And that's what that's the kind of waves air is. Yeah, that's the kind of waves that go through the air. They sort of pump the air. I can show that, I think, with my slinky, if I can borrow Ron again. What do we do with the slinky, Ron? You hold one end. I'll get back up here. Get it all on the table, Ron. I think you can see the impulses moving back and forth this way. The waves that we demonstrate with are sinusoidal waves like that, simply because they're much easier to draw. In any wave, we're talking about three elements. We're talking about frequency, amplitude, and we could talk about wavelength. But something more important that we seldom talk about when we're dealing with sound alone is what we call timbre. Spelled that way, but pronounced timbre. This has to do with the complexity of the wave. If we produced a wave like this, a sound wave like this, it would be very uninteresting and very plain. I think we can do that if I have the right connections here. Auxiliary. This one.
Give me a hard time here. There.
Oh, okay. Thought I was on it. This is called a frequency generator. I can change the number of cycles per second. In fact, while we have this hooked up, we could test your hearing. The human ear can normally hear from 20 cycles per second, or 20 hertz, up to 20,000 cycles per second. That's if you're young and in good shape. If you're 30 or better, your hearing has probably fallen off to about 15 hertz, or 15 kilohertz, 15,000 cycles per second. That's one of the sad ironies of life. By the time you can afford that good hi-fi system, you're too old to appreciate it. Only your dog can enjoy it, or your cat. That's a multiple, and it crosses like that. Whoa, baby. Notice how symmetrical the waves are. They're very uncomplex, and they're not very musical. No, I can't remember if I have this on the scope or not. Is this on the scope, Brian? Oh, I got to change that. All right. Okay. One of the problems of getting older, it's nice to be able to get older. It beats the alternative, but one of the problems that you get to be forgetful. Is that on the scope now? Yeah, okay. Speech patterns are very specific. They're not the sinusoidal waves that you might you might expect. But they're, let me see if I can get that. I think you can, if I don't talk too loudly, that'll probably be within the range of the settings on the scope now. If I pronounce the vowels, A, E, I, O, U. Anyone feel like singing? We can see the pattern. What you notice here is that we've deviated from that very smooth sinusoidal waveform to a very complex wave. That's necessary when we transfer our attention to music rather than just pure sound. Well, when we talk about music, or we extend our discussion of sound to music, the most important added element now is what we call timbre, and that is the wave complexity, how complex the wave is. Instead of just a plain sinusoidal wave such as this, we really have a wave that's doing something like this. And that particular pattern has to do with a number of overtones and additional frequencies with which something vibrates. When there's a vibration, there's very few things that vibrate simply like this. There's generally multiples of that waveform, so that we end up with something like this, then perhaps another like that, and another like this. So altogether, it produces an effect something like this. So when a body vibrates, it not only vibrates according to what we call the fundamental, but it vibrates with additional frequencies, and the number of frequencies and their relative intensities and their relative combinations all contribute a very specific sound. A good violin would have a different structure than this. It would have what we call F-holes that follow somewhat the contour of the instrument. It has a sound post that transfers sound from the front to the back. This does not. There might be a cigar still left. But just the way the thing is built and structured and varnished all contributes to the characteristics of those tones. Let's see what else we're going to do. Yeah. Well, if someone asked you what music is, what would you tell them? What's your idea of music? Well, when I was in high school, I worked in a garage with 2 Air Force mechanics, and I learned to appreciate automobiles. Well, I love mechanical things anyway, and to me, the sound of an idling engine, well tuned, is music to my ears. Well, maybe to you a babbling brook is music, maybe a chirping bird. Maybe certain words from someone dear to you, like the fellow that sits on his porch after work, tired and waiting for the evening to start, and his beloved comes up behind him and whispers those 3 beautiful words that every man longs to hear. Supper is ready. Well, to them, that might be music. Words can be music. But music essentially has these characteristics, but in addition, there's 3 other things that are very important, and it has to do with what we call the envelope of a sound. It's the attack, the sustain, and yes, and the decay. How fast a sound begins, how long the duration of the wave is before it begins to decay. That is, if we looked at a number of typical waves, a square wave would look something like this. If I showed you this on the oscilloscope, it would look rather peculiar because you wouldn't see this part. You wouldn't see this part. You'd only see this line, this one, and the next one. You'd only see those because the trace happens too fast as it drops and falls. A very rapid attack would look something like that, and a very rapid decay would look something like that. On the other hand, a wave that did this would have a slow attack, a moderate sustain, and then a fast decay. There are a number of different ways that are used in music. One is the sinusoidal wave, as we said. One is the square wave. Another is the rectangular wave that would look something like this, a long peak. And so on. And then there's the sawtooth. A triangular wave would be like this. I'm going dry here. Would look something like that. Sawtooth would be a fast attack and a quick decay, fast attack and quick decay. And a reverse sawtooth would be this, something like that. All of these have different sounds, and when you combine them, they give the characteristic sound of a particular device. For instance, a string, a violin can only produce odd harmonics, odd multiples of its basic frequency. Woodwinds and clarinets and the other instruments all have their characteristic shape of wave. Sound patterns from a voice have characteristics. If you're looking at a sound print from a person's voice, you may find similarities between two voices, but there are certain pronunciations or certain vowels or certain things that would be said that would at that point show a difference. It's like handwriting. Comparing two sets of handwriting, you might find that everybody makes their D's and T's the same, but the secret's in the K. The way the K is made is very individual, perhaps. And that identifies a particular handwriting, and so it is with sound. A particular sound can be identified by its particular pattern. I have a lot of notes on scales and things like that, but I don't think we want to bother with that. It looks too heavy for the hour. Right now I would like to show you what some wave patterns look like with my son's assistance, Brian. We'll try some different sounds.
Oh, right here.
Yeah, there's a problem with that. Well, no, it's getting trouble.
Why didn't you say so? It's very odd. All right, I'll do.
Well, hold
No,
it.
I got it. All right, hold it.
Well, what's supposed to be first trumpet?
Yeah, that's good.
Yeah. Well, give us a trumpet sound. We'll look at the pattern for that. That's not a trumpet. No, that's not a trumpet. Wait a minute, we're not getting a single. Yeah, we're on. Okay. Okay, give me a sustain.
There, that's fine. Too loud? Not loud.
It died on me. It died.
Yeah, we'll let Patrick
I'll drop it. Okay. Oh,
Got it?
I know what the problem is. That's a, yeah. It's a, no. Drop it. Yeah, okay. Got it now if I can hold it.
So let's try trumpet.
Okay, trumpet. Oh, yeah, that's a trumpet.
You seeing the shape?
Yeah.
All right, let's try something more mellow.
Yeah, that's a good. Try to hit the same note, the frequency, then I don't have to
All right,
Let me get that.
Flute?
that's a flute.
Sounds-
Violin.
It looks pure sinusoidal.
No, you can see the complexity in that wave. Yes, or cello. Well, hold that if I see if I can stop that. That's a multiple of the frequency. Notice that that has a fast attack, a sudden burst, then a very slow decay. Okay. Fast attack, fast decay, which is typical, not only that, but it's typical of a percussion instrument which produces, well, drum and a cymbal borders on noise. That is, there's not a regular frequency. It depends on how hard it's hit, where it's hit, and so on. That's a fairly sinusoidal wave. What we're seeing there is multiples. I can't arrest the frequency, so that it. There we go. Okay. That's a harpsichord. Look at the complexity of that one. Okay. Thank you, Brian. Let's just stay there. I'm almost done. Electronic music started probably in 1929 with the advent of the Hammond organ, which for years was the standard electronic musical instrument. Hammond was an electrical engineer who worked with designing clocks, and he discovered that a coil of wire used as a pickup, I'll attach that to my meter here. It's a very sensitive meter, and we couldn't get a bigger meter to respond, so you might have trouble seeing this. But if I pass a magnet across that coil, I can get the meter to respond, indicating that I get a small blurb of current. Can you see that from where you are? If I had a wheel with a number of notches on it, and it was magnetized, and I rotated that past the coil, then I can get a number of impulses per second. And as long as I have the right number of impulses per second, then we can have a particular tone. Each tone has its own frequency. We call that well, if I don't lose my glasses, I lose my pen. We would recognize that as perhaps pitch, but frequency isn't the only thing that determines pitch. The complexity of the wave, the intensity of the wave, the intensity of the harmonics, all these things affect pitch. Pitch is subjective. that's what we hear. Frequency is what the thing is doing physically. So in music, there are a number of characteristics that are essentially subjective. That is, they depend upon individual interpretation. But the most important thing is this timbre, which is sort of the personality of a sound due to the complexity of and the condition of the wave. I think that's enough for one time. The scales are quite mathematical. Of course, in order to have music, you have to have a musical scale. The musical scales have gone through a great deal of change over the years. A name you might recognize, though, is Pythagoras. You remember him for the Pythagorean theorem, you know, c squared is equal to a squared plus b squared in a right triangle. But he was one of the first to actually notice the mathematical relationship between tones that sounded good together, that sounded, I would call it harmony, or sound, I can't think of the term I want, but anyway, he noticed mathematical relationship, and then through several other changes and other people adding certain relationships, we finally came down to the scale we use today, which is the tempered scale. There was an original problem with the scales that were developed because, let's say, a C sharp wasn't the same as a D flat. Well, that's difficult for a piano. You'd have to have a different key for C sharp and D flat. And as Victor Borge, a great noted musical historian, said, pianos were developed right after they didn't have any. And that was one of the original problems. But the even tempered scale has divided an octave of 12 notes into even frequencies, so that a C sharp now is a D flat. The problem with our modern musical scale is that some of the combinations are not really harmonious. That is, the waves do not agree with each other completely. And so some of the chords, some of the music is not quite as harmonious as it would have been if we used the Pythagorean scale or the just diatonic scale. But the compromises are very small, and of course it makes for a great convenience. In a piano, it would be impossible today to have a piano with separate keys for C sharp and D flat, or G sharp and A flat, and so on. All the things we've talked about here having to do with frequencies and vibrations has a great deal to do with the piano. A piano, and this is the Piano Man, is designed in such a way that much of the sound that is generated is augmented by the soundboard, the spruce backing of the harp that mounts the strings, so that there's a impedance match between the strings and the ear. If it was just the strings alone, there'd be nothing you could really hear very well. One of the clever things about electronic instruments is that today, because of this thing we call digital voicing, because of the advent of transistors and then integrated circuits, we're able to store literally millions of signals in a very, very small space. And let's see, a common computer has 3.2 gigabytes, that is 10 to the 9th bits of information it can store. Now that's quite a bit. If we take Hammond's original revolving wheel tone generator, then what you get are sinusoidal waves like that. And as we've shown that they're quite uninteresting. What we need to produce a different tone is a different wave shape, perhaps, depending upon the instrument, and the overtones in proper number and in proper intensity. Well, to do that with a Hammond, it had to be done electronically with transistors, with resistors and capacitors, and the sounds could only be approximated. Today, however, when we have a very complex wave, such as like this, or some you've seen on the oscilloscope there, One way to copy the sound of a particular instrument is to take that particular moment in time and register that voltage, take another moment in time and register that one, and so on. So the digital instrument, actually, to copy a sine wave, would look something like this. It would do it in steps. These would be all increments that are stored in a chip, and then you could get a sine wave. Then, of course, you can do the same thing with a square wave, and with modern electronics, you can combine all of these. So to get a very faithful sound, we would need to be able to copy that wave precisely, and we can do that, store it on a chip, so that when you ask for the sound of a particular instrument, that's what you get. You get that precise waveform. In one of these instruments, I've seen an electronic piano. A mechanical piano, when you press a key, you not only get the strings, you get all the other strings vibrating harmoniously with them in multiples of that frequency, but you also get the key clicks, that is the mechanical sound of a piano. You don't notice that, but that's part of the timbre that you hear. These things actually record that mechanical sound and add that to the waveform. You're not conscious of that, but that's one of the things that makes them so faithful to the original sound. I think that's about enough. Do you have any questions that I can't answer? Yes.
Hi, Dave. Ken Wilson.
Yes, Ken.
First, I just want to say this has really been really interesting, and thanks a lot. I'm stuck on this. I hope my question here makes sense in a couple of parts. Are all sound waves symmetrical?
If by symmetrical you mean something like this, no. If you mean are they identical, yeah, I think what you're asking is the next wave the same as this one? Yes. Yes.
So, okay.
That's repeated over and over and over. However,
does turbulence make sound?
that's like the tree falling on the floor. No, yes, it does. It adds to the timbre. Timbre, sorry. I have trouble saying timbre when it's spelled timbre. But it does add to the overall sound. In fact, on wind instruments, because you're changing the length of the tube by either valves or in the trombone, the slide, you have to have compensation for that. So you see in some of these complicated instruments, little curlicues of tubes, looks like complicated plumbing. That's to compensate for the changes that occur because you're changing the length. It gets to be quite complicated when you look at the design of an instrument. But this business of timbre that we've been talking about and the wave shape does change. If you blow harder on an instrument, for instance, you've heard someone practicing a trumpet and you notice that in order to start, or the novice has a hard time getting a good even note, and it changes on them when they're blowing. The way you blow, the way you purse your lips, all have to do with generating the sound in a musical instrument. Even in a violin, the way the fingers are moved across the board and the way the instrument is bowed even makes a difference in what the wave shapes or the content of the harmonics actually are. That's what makes a good violinist better than a poor one. The techniques that produce the harmonious overtones that are pleasant to hear. Any other questions? Yeah.
When we speak, use the musical term counterpoint, as in Bach. What is going on there in terms of the physics of it?
That I do not know.
Just curious.
Anyone here know? Then we don't care.
Have you ever heard of the, I believe they're Tibetan monks that actually produce two tones in like a chord, a sung note and a droned note? Do you know, is that an overtone? Is that the same as somehow setting up a
Yes,
sympathetic
it
vibration?
would have to do with resonance, yes.
It's probably harmonic. It's a harmonic?
Yes.
It sounds really
Overtone's the same as a harmonic, yes.
Okay.
Yeah.
So it is the same effect
Yeah.
as that sort of doubling over, that layering of the,
Yes.
of the wave.
Yeah. Also, acoustics have to do with the room that you're performing in. For a singer, if there isn't reverberation or a reflection of that sound, for instance, at a particular note, if the singer isn't conscious of that same note coming back, it's difficult to intone the next one properly without that reference. So without a good reverberation, a singer has difficulty in what we call placement, putting the notes where they belong. Yes, sir.
I would like to hear Brian.
Well, we've arranged for that as we close. I think we're about done. I'd like to express my appreciation again to Charlotte Gifford for inviting me to participate in the lecture series and to the Learning and Teaching Committee, and to Ron for his expert help. We've done these things many times together, and for my son Brian for giving up time to come and demonstrate a few things for us. And oh, and yes, and my grandson, John Ryan, for loaning me his piece of equipment. And I thank you all for your kind attention. I've enjoyed it. And as the Firefly said as it hit the windshield, I'm delighted.
Thank you.